Pause. We didn't actually
introduce
ourselves.
So, Ben, who are we to tell people things about Rust?
I don't know, John. Who are we to tell people?
Well, we're both mostly nobodies, but if we had to give credentials, so I am a grad student at MIT. I work on fast research databases in Rust. I also maintain a bunch of libraries, and I do live coding streams in Rust.
Yeah, and I do various organizing for the Rust communities. I do moderation for various Rust forums and that kind of thing. I answer questions. I do some triage in the bug tracker. And so in my case, especially, I organize the Boston Rust meetups where we've begun every 6 weeks, just going over the newest release notes kind of like there before any of our talks or kind of like beginning for the night. And they've been very well received. And so I thought kind of as an inspiration, so hey, why don't we make a podcast out of this? Kind of like just turn it into a discussion forum real quick.
Yeah, let's do it.
Yeah.
We, like many others, were big fans of Chris Krycho's new Rustacean podcast.
Mm-hmm.
And when we heard that it was ending, we were sad to see it go because it's been such a good influence on the community. It's been a good source of news. It's been a good source of educational material for Rust. And so we wanted to find some way to continue that into the future. And so we ended up in the position where we started brainstorming, like, how do we do that? How do we go about doing this without Chris or without stepping on Rustacean, but just starting something new and fresh that could bring the community forward.
And there's a bunch of steps that are like required for doing a podcast that aren't kind of just the recording part. There's the hosting of it, there's the making the show notes and uploading and recording, audio processing, all of that nobody actually wants to do. So that's why we're here.
Yeah, I mean, we figured out that there's a lot of appetite for Rust content out there, and we hope that we could be some of those people to bring that forward. And so, Ben, you came up with this idea of let's start a podcast.
Yeah, so let's start a podcast, or at least start a meta podcast, if you will. So yeah, the idea is there are a few podcasts in the Rust community that have gone on in the past. There's, I think, what's Manisha's? Request for explanation.
Yeah, that's the one, yeah.
That one. There are some other ones, I think, kind of maybe from Florian Gilcher or roundabouts, thereabouts.
Yeah, Rust also comes up in other podcasts as sort of just frequent appearances.
Mm-hmm.
But we figured it would be good to have some collective way of both encouraging people to make new content and just having a way for those who want to produce Rust podcasts to come together and sort of brainstorm ideas and collaborate on this process, which is relatively large and complex.
Yeah. And so kind of like if you're new to podcasting where it's like, what audio should I use? Like what mic setup do I need? We have all the information. We have help from Chris Krycho himself, graciously offered to give us all of his expertise in making this the best podcast we can. And not just podcasts, but we want to also help others to make podcasts here. So we have a Discord. We have, hopefully by this point, when you're hearing this, a Twitter and a GitHub account. Our tentative name right now for this kind of overall umbrella effort is Rustacean Station, which...
It's good.
It's good.
I like it.
It's pretty good. Yeah.
And in theory, you should be able to look at the show notes below or to your left or right or however your app is configured. You'll find a link to those things where you can catch us later. And if you have an idea for a podcast that you might want to do, or if you have feedback on this episode or particular things you want to see, then reach out and we will try to do our best to make that happen.
But then what is this right here, this podcast that we're doing right now?
So we try to figure out where to start because it's always hard to start. And we figured that one of the easiest places to start is with a new Rust release, which 136 was just posted. And so let's take a look at what's new there. The first thing that appears if you look at the big announcement for 136 is that Futures has now been stabilized.
Well, something has been stabilized. Standard future module has been stabilized. Futures doesn't mean quite the same thing it does in Rust as it does in, say, JavaScript or C#. Do you want to talk more about that?
Yeah, it's true. Rust is in this weird place where futures encompasses a lot of things, and it means different things to different users and developers of Rust. And as opposed to promises in JavaScript, for example, Rust futures are really lots of different components that come together. And the one that was stabilized in 136 was the future trait. And the future trait is sort of the heart of the Rust asynchronous computation and I/O story. The future trait is essentially just one thing. It tells you how you can ask something to make progress on something that hasn't finished yet. Or to unpack that a little, in other languages, like in JavaScript, promises are some value that may or may not be ready for you to see yet. It might be a network request that hasn't finished yet, a file you're reading but hasn't finished, input from the user that hasn't come in yet. And at some point, that value is going to come back to you and be ready, so to speak. And the way that works internally in JavaScript is the JavaScript engine has some way of making all of the promises in the world move forward, and you can choose to do something when that computation
What
is
is the
finished.
engine, do you mean? Like a V8? Is that the engine? Like we use
Yes.
Node, potentially, so...
So Node or V8, Node uses V8, so Node uses V8's sort of event loop, basically. And what that will do internally is it will talk to the operating system and see when different sort of sockets or files or input channels from the user are ready. And when they are, it will let the promises that depend on those make progress.
Now, people who are a bit knowledgeable about this whole effort in Rust, I mean, probably heard about, like, there's Mio and there's Tokyo. And so, like, where does that compare to what, like, Node supplies for this kind of effort?
So in the Node ecosystem, or in JavaScript in general, you don't really have a choice as to how your promises are executed. They just sort of magically make progress behind the scenes, and that's done by the JavaScript engine. In Rust uses a poll-based model instead. So you have to have something that decides that it checks whether, or it tries to make progress on some computation, and it every now and again goes and checks that thing to see whether more progress has been made. So for example, if there's a network stream that you're trying to read from, something has to ask that network stream, hey, do you have more stuff for me? And in Rust, that is what we often call an executor. So an executor is something that has a bunch of futures, like knows about the futures that exist or that you might be waiting on, and then it will go around and pull them to try to make them make progress. Tokyo is an example of such an executor. There are other executors that are also being built. And these executors, you can sort of mix and match, and all of them work with the future trait.
Okay.
And then Mayo is an example of a reactor. So a reactor is often called a notifier or a waker. They're not quite the same, but the basic idea is you don't want to pull all your futures in a loop, right? That would be very inefficient because now your computer is spending lots of cycles just asking the TCP channel or
Are
whatever.
we there yet? Are we there yet? Are we there yet?
Yeah, exactly. And you don't really want it to work that way. Instead, you'd rather have the operating system tell you, hey, I just got a packet for this TCP stream, you might care. And so that is what Mayo gives you. So Mayo abstracts over multiple different operating systems and basically gives you a way to tell the operating system, here are a bunch of things I care about. Let me know if anything happens to any of them. And then Tokyo combines Mayo with the future trait in such a way that a future can say, I'm blocking on this resource, and here's how you tell me to wake up later. So this is, if you look at the future trait, you'll see that the poll method takes a context, and the context is associated with a waker. And a waker is essentially sort of a callback that the executor can use and pass around to, for example, tell the operating system, when new data comes in on the stream, notify this future so that I know to continue executing it.
Let's back up here, kind of like ring in the weeds a bit right now, where it's like, this is all very complex. Imagine I'm somebody who, like, comes from JavaScript. I'm like, listen, I just want to know how to, like, do asynchronous stuff. It's like, how can I use this future trait to do whatever? Like, what do I need to do?
Yeah, so this is where it gets a little bit complicated. And this is where the difference between futures and Rust, the way we think about it, and future the trait become a little bit different. So future the trait stabilizes sort of the core primitive for this kind of asynchronous stuff in Rust. Whereas when you're going to use futures, often what you will do is you will want to use the async and await keywords. So these are things that have not been stabilized yet and that are targeting a later Rust release. And they provide a convenient way for you to write code that takes a future and says, wait for this future to be done and then do this other thing afterwards. And it also provides you a mechanism for writing futures yourself to say, here's a function that is going to do things like network requests. And so you might need to wait for it to finish. It's not going to return immediately. And so that's something that will be stabilized later, but has not yet been stabilized.
Okay. So for example, in JavaScript, I might make a promise and then use the .then method on that to like chain things together, operations, callbacks, and this is not the same thing as that.
Not quite. So the future trait itself is only the poll method. All it does is it gives the executors a way to make progress on futures.
Okay, it's very bare bones.
It is very bare bones. And the reason for this is, the reason it's been stabilized on its own and why that is useful is because it means that now the ecosystem can start to come together around that standard library.
So Tokyo itself really wants to be using this.
Right. And any other executor, or even if you're in a no-stud environment or like an embedded device or something, you might still want to centralize around the standard future trait. Because it means that later on, when we get async and await, when we get things like combinators, so these would be things like and then or map or else on futures, all of them will work with the same core primitive and, at least in theory, be able to interoperate.
Awesome. Very cool. There's also a task waker API. You mentioned Mayo before in terms of like, is this new API in this release, is that what Mayo would use? Do you happen to know?
So the task stuff that's been stabilized is a little bit more into the weeds, but I'll try to give you a high level overview.
Yeah.
So when you call poll on a future, the future has one of two choices. It can either say I'm done, here's the value, or it can say I'm not done. And it's represented by the return type being either, there's an edom called async, and it is either ready or not ready. If you're ready, that means your value can be returned. If you're not ready, that means that the value is not ready to be returned yet. If it's not ready to be returned yet, the future needs to have some way to indicate that it's ready to continue. Because as we mentioned, you don't want to just pull it in a loop. And the task stuff is basically the way in which a future can say, call me here when I should try again. So for example, you could imagine a future that wants to yield in a loop. Like the most trivial example of a future is one that is never ready but always tries, right? So what that would do is it would call, it gets a handle to its own task, which includes a waker when you call poll. It immediately calls notify on that waker, and then it returns not ready.
Okay.
So what that means is it immediately marks itself, its own task, so to speak, as ready to be polled again. And so the executor with such a future is just going to call poll in a loop on that future.
Okay.
And you can imagine that instead of immediately notifying itself, that notify or that waker is sent off somewhere else. And that somewhere else is eventually going to notify the task that is that future. So you can think of a task as a particular instance of a future.
Okay, so in this case, this poll module with these wicker, it's kind of more for the building block, like you said. It's not made for like an end user necessarily to worry about. It's kind of just a detail.
Yeah, I would think about the future trait and about tasks as more something for library authors to deal with and executor developers to deal with, more so than end users. My guess is end users will sometimes come across the future trait in the sense of they're given something that is a future, or there's a library that returns something that's impl future. But usually you will be writing async functions, async closures, and using the await keyword.
All right, so and that comes out in 1.38, which is in 12 weeks from this release anyway. So yeah.
It's exciting.
Something to look forward to. Very cool. Let's talk about something else that's new in this release, the alloc crate. So this is a new crate in the standard library, kind of a new division of the library. And so again, as an end user, why would I care about this?
So alloc is interesting. In the past, if you wanted to not rely on the standard library, perhaps because you're on an embedded platform, you only really had two choices. You had core and you had all of the standard library.
Mm-hmm.
Core is very basic. It doesn't require anything from its environment. All of it is just code that can run in isolation. Whereas the standard library has a lot of requirements on its environment. It needs support for things like system calls and timers and random number generation and allocation. But all of these were grouped together. It was all or nothing.
Mm-hmm.
Of course, in embedded platforms, it might be easy for you to write an allocator. It might be relatively hard for you to provide all of the system calls for file system operations.
Or threading or...
Right, exactly. And so the alloc crate or the alloc thing, the alloc division, so to speak, is a way to say, here is stuff that only depends on allocation. And the prime example of this are most of Rust's collections and data structures.
Like Box, especially.
Box is an example of this. RC is another example of this. There's vec, of course, vecdq, binary heaps, B-tree maps, all of these things that they're mostly just code, so they don't have external dependencies, except for they need to be able to allocate. And that is now what the allocate provides you. And this means that if you are on an embedded platform, you implement a memory allocator, you can now get almost all of the Rust data structures and collections immediately for use in your application.
Cool. I want to kind of like back up here to a bit, kind of like just to give a more like high-level overview of what core is. And so back in the day, we have obviously the standard library is a thing. And like you said, on some targets, some hardware, not everything that is provided is useful or really possible very easily. Standard library assumes that all of the things in there are kind of like you're on a platform with like, again, file support, modern kind of like, you're on a desktop machine, say, or a server machine, and not say like a $1 board that has like 10 megahertz processor on there somewhere. And so the idea was, well, for those people, they can just kind of like, we have a new flag, it's called no_stud, and you can just not have the library at all. That was a bit too far, because there's plenty of things in the standard library that are perfectly fine to use without on these platforms, like option, say, or like slices, which are all just usually on the stack, and even without a heap to allocate on, you still have the stack to work with. And so this is where core came in. Core is a subset of stud that doesn't require any of the extra stuff that you might only find in a more quote-unquote modern or full-featured piece of hardware. And so really what this does is it kind of makes it a bit easier to write libraries that can target either core or stud, because before, if you used, say, a single vec anywhere in your library, well, you couldn't target only core. Now you can target core plus alloc, which makes it easier for no_stud crates to, if they want to implement alloc, or an allocator for themselves, now they can use your crate.
I think one way to think about this is libraries can now specify their dependencies with a little bit more granularity.
Yeah.
You don't have to say, I require all of the standard library, when really all you need to do is allocation. Mm-hmm. I don't know whether we'll see further subdivisions of this, like I only require threading, or I only require randomness. I don't think we'll go quite that far of saying like slice the standard library up among every dimension, like feature flags.
And to some degree start something like, feature flags almost. And so who knows what we'll see in the future. That would be very interesting, kind of like to just have a cargo.toml, a section in there where it's kind of like, what parts of stud do I actually want, or features thereof?
Maybe one way to explain alloc is it's the standard library, but with no default features and with the alloc feature.
There you go.
So somewhat related to this, we also have a new data structure that's been added to the standard library. Or rather...
Well, not really.
It's a new implementation of an existing one.
Mm-hmm.
And so this is the standard collections HashMap. Its implementation has been completely replaced by a new external crate called hashbrown. Mm-hmm. Do you want to talk about hashbrown a little?
Sure. So hashbrown is an adaptation of a hash table implementation from Google, I believe, called Swiss table. And there's a few different improvements here. There is I think a blog post somewhere, I'm sure, discussing more of how hashbrown compares to our previous hasher, which I'm not sure if there was a name for it was kind of Robin Hood hash. And if you aren't versed in hash map theory, this all means nothing to you, so let's not get too involved in that. But the bottom line is that the new hash map implementation, so any code previously using hash maps should now be using, have 8 times less overhead in memory for storing keys, and it should see up to a 2 times performance improvement.
So one of the things that's cool about this is that the Swiss table implementation is just a lot more optimized. It's sort of been thought through very carefully. And in part, one of the things that allows you to do is to use SIMD instructions. So these are, for those who aren't aware, they're effectively a way to have your CPU look at many pieces of data simultaneously. This means that if you do lookups, for example, you can check multiple entries, multiple buckets, multiple things in the hash table at the same time, which significantly speeds up things like lookups, removals, basically anything that needs to search.
And this actually happened before, I believe. This isn't the first time that we've totally redone something in our HashMap implementation where I think we might have changed the default hasher before, say from siphash 2.4 to siphash 1.3. So this is it's kind of par for the course, but what's different in this case is that this new HashMap crate is not actually living in the Rust repo. As you mentioned, with the cargo.toml segue there, is that this actually is living on Krycho.io. We actually, to build the compiler, or to build the standard library now, we actually leverage Krycho.io, which is really cool, because it means that even, say, one thing we forgot to mention previously from the previous topic was that in the alloc crate, we did say you get some collections, but not all. Notably, hash maps aren't one of those. And so if you just get the alloc crate, you don't actually get hash maps. You get pretty much everything else but hash maps. And the reason for that, according to our research, which is just asking Simon Sabin on Aerocity, is it requires randomness for siphash, which is the default hasher. It is a cryptographically secure hash, and so as a default hash, it is very safe to use to expose, it is more safe, say, to expose to a untrusted input than other hashes. But because of that, it means that alloc-only crates can't use it. But say if you were using no core, or no stud, a core-only crate, and you wanted to just totally import hashbrown, you could. And you would have the same code that runs on everyone else's machine, as long as you provide some, hasher that doesn't require randomness.
Yeah, I mean, it really means that you can use the HashMap implementation from the standard library in your own code directly, even if you don't use the standard library. And as you mentioned, one of the reasons that's neat is the crates.io version of hashbrown has a feature flag that is no stud. And when you enable this flag, it will not bring in the default hasher with its randomness requirements, which in turn means that you can use it even in crates that only have alloc.
Yeah, very cool.
Another thing that came up in 136, which might confuse some people, is there's the deprecation of MaybeUninitialized and the addition of something called MaybeUninit. And this is a somewhat subtle change that has to do with the safety of Rust code. To quote directly from the announcement, imagine that you have something like a Boolean, and you say, let x colon Boolean is equal to MaybeUninitialized. This turns out in Rust to immediately trigger undefined behavior. Because when you say MaybeUninitialized, what you're telling the compiler is just give me some memory and don't set it to any known value, and I'm just going to treat it as if it's of any type T. And
might be useful to compare it to C and C++ here, where in those languages, when you declare a variable and when you initialize it, they can be different. Same as in Rust, but in Rust we have mechanisms at compile time to enforce that you actually initialize it before you use it, unlike in C. And so in C, you can just say int x, semicolon, next line, and then x plus 2, and who knows? Something might happen. There's some memory at x at a location that will be read, and then something will happen. And so Rust prevents that, but sometimes it is useful to be able to do this. And so in unsafe code, we do allow this MaybeUninitialized to do some of the same patterns. Say if you have a really big vector or array where you don't want to initialize them all to zeros, which would be the safe thing to do, I think the default thing to do. You want to read in memory data over time, initialize it all at once, and avoid the setup step. It can be much faster that way. And so normally you use this to do that. But there's now a new way of doing this.
Yeah, so it turned out the old way was really unsafe because sometimes a type, for example, has a requirement of its value. Like it has, for example, Booleans need to be 0 or 1, and the compiler relies on this. But this old pattern didn't allow you to, it allowed you to violate these guarantees.
It kind of almost forced you to.
Yeah, you didn't have a way to really work around this. In the new pattern where you have this MaybeUninit type, the MaybeUninit type, we won't go too much into the technical details, but the idea is that you get back a type that the compiler knows might be uninitialized. And so it doesn't treat it with the same requirements as the sort of backing type. You can almost think of it as an option. It's not quite an option, but you can think of it as something that either has been initialized and therefore has a legal value and can be treated as such, or it does not have a legal value yet, and therefore you can't treat it as that value. And then you have a way on MaybeUninit to say that the value has now been initialized, and now I want to get it back as a T.
Mm-hmm. And what's cool is that this isn't like, you make it sound almost kind of like compiler magic, where kind of the compiler just knows these things. Actually, the implementation is surprisingly simple, because Rust already has a feature called C-style unions, which, if you're not familiar with C, imagine kind of enums but with no tag. And so the idea is, here is a piece of data that can be either this or this. And so whereas kind of, you mentioned an option before, an option is either something or nothing. You can have the same thing with this MaybeUninit type, but nothing actually means nothing in this case. And so in a way that is a bit different from none. I don't want to get into it right now.
Yeah,
zero-size types versus uninhabited types. So
the way, if you're coming from C-style languages, the way to think about this is, in the MaybeUninit case, you don't need to store which of the two cases you're in.
Mm-hmm. Yeah, so at the end of the day, it's only a union, and one of the members is nil, the open close parentheses, and the other is your data that you want to have. And so it is much easier to understand. It is like well understood already how this works in the compiler, and so it's easy to specify. And so in this case, that was really the clincher for this, because like you mentioned, like this is we believed it was safe before, this mem uninitialized function, but it wasn't. And so what changed? Like how did it become unsafe? Isn't the whole point of Rust that like we can control unsafety?
So this is something that I'm sure there are many of the listeners as well who are like scratching their head and being like, oh, is Rust all a waste? Like even the standard library is broken. And I think it requires a little bit of I don't want to say faith, but
what does require faith is the thing.
It's true, but what Rust does is it tries to encapsulate unsafety, right? The idea is that if you have to do something unsafe, then there's a limited stuff of things you're now allowed to do. And the primary one among them is you're allowed to treat memory as of a particular type. You can dereference raw pointers, essentially, and you can cast between different types that are the same size. And the intention is that whenever you do this, you try to come up with a safe encapsulation, and you basically have to convince yourself that the encapsulation you provide is actually safe. In the case of mem uninitialized, what really happened was the standard library thought that the interaction with the compiler was one way, and it turned out that it just wasn't safe to make those assumptions. Mm-hmm. And I think the reason we realized this was because there's been a lot of work recently studying precisely the effects and implications of unsafe Rust code. There's been a lot of efforts, the unsafe, what's it called? The Unsafe
Code
Guidelines Working Group.
Yeah.
That have been looking really into what are the exact requirements of unsafe code? What does it mean for unsafe code to actually be safe or to be used safely? Mm-hmm. And what are the requirements of things like memory layout in Rust that people who write unsafe code can rely on? What are the guarantees, essentially? And going through that principled process of figuring out exactly what are the guarantees and requirements is what has led to the discovery of this particular issue. There was a related one recently, which was the stabilization and immediate deprecation.
A day later.
Yeah, a day later of the type ID trait.
Yes, I believe so.
Yeah, I think it's called type ID. And the basic idea here was you could take a type and call type ID, and you get back a sort of opaque identifier of that type. And you could later use that opaque identifier to take a pointer and cast it to that type with basically wrapped in an option. So if that type was of the appropriate type, you got back a sum. Otherwise, you got back a none saying this pointer is not of that type. I'm going to refuse to cast it for you. And this turns out to be really broken because type ID being a trait, you could implement it for your own type and return the discriminator for some entirely different type, and this breaks everything. And so this is the compiler, or not the compiler, but the standard library trying to provide a feature that was initially thought sound.
Yeah.
And then it turns out it can really be broken.
Yeah, when it comes to unsafe code, the library has to work with the compiler too. Like the language and library aren't really separable in that case, because there are assumptions that the language makes about what it can do with unsafe code, and when those don't match up with what a library actually provides, you have problems. And so in this case, as of 1.0, which is where the MaybeUninitialized function comes from, we believe that unsafe Rust provided certain guarantees, but it hadn't actually thought about it enough. And so the question here, I think, that rises next is, like, well, how do we know anything has been thought about enough then? Like, what other things might be currently that were marked unsafe but are actually, like, you know, can't even be used safely in the first place? And it's a good question. We hopefully think it's none of the current things besides this one, but it is part of the, it's a crucial question to what Rust is. And so, like, fundamentally, until Rust has some kind of, like, specification for what unsafe code can do, it's kind of like formal proof that all this works. The idea of Rust is, hey, if it's broken, it's our problem, we'll fix it. Okay, and so it's really a promise. Like, Rust here is like promising that if there is some kind of undefined behavior potential in safe code, that is the thing that the Rust developers themselves will find a solution for. And so until that time, the way that you, like, know in unsafe code, if what you're doing is, like, permitted, it sounds absurd, but the way that you know is, well, does it happen in the standard library or any of the, like, blessed quote-unquote libraries that the Rust maintainers maintain?
It is true, though, that unsafety is the biggest, I think, problem area for Rust guarantees, because
that's the entire language. That's the point.
Well, I think we can be a little bit more charitable than that, in the sense that most of Rust is written in safe Rust. Most of the standard library is written in safe Rust. Most of the library crates are written in safe Rust. And what unsafe lets you do is, in the particular cases where there are invariants that you have maintained as the programmer, that allow you to do something that you believe is sound, you can tell the compiler this is the case, even though the compiler couldn't check it itself. It's really a way to provide the compiler with sort of human-checked invariants. And that is very powerful, right? This is, all of C is like this, right? So I think saying that not all code has to be unsafe is still a big step up. The fact that you do have to write unsafe code some of the time means that we really need to figure out what it means to write unsafe code and what it means to go from unsafe code to safe code. The Nomicon has been really good about documenting some of the dark corners here.
It's required, essentially, if you're writing unsafe keyword in your code.
Yeah, exactly.
To read Nomicon. Really.
I think the Unsafe Code Guidelines Working Group is a really important initiative here to really nail down what the requirements are and what the guarantees that are being given are. But I think this is an open problem area for Rust, where
it's a totally legitimate criticism to say, hey, like you mentioned, human invariants enforced by the humans, but like the humans might not even know necessarily what the invariants are. Obviously, as of 1.0, when this function came out, this MaybeUninitialized function, like we thought something was true that turned out not to actually be true or to be enforceable feasibly, but what we could do. So yeah.
Sorry, go ahead.
No, there are a few people working on this. So there's Ralph Young is the most prominent in terms of, like, if you ever, like, go on the GitHub issue tracker for Rust these days and you see any kind of, like, discussion that it all involves, like, the crazy memory unsafe stuff, he'll be in there somewhere being like, how can we formalize this? Like, looking to the future and trying to say, hey, like, let's make sure that we add new features and new library methods that we actually can formalize someday. So I think the biggest thing I saw last year was Pin, another, like, building block for futures in the future that I probably anyway. And that's an epic GitHub issue thread, like hundreds of very dense comments between him and Without Boats, just like talking about like what is possible to, like, you know, given Rust's memory model of what we, like, expect to specify someday. and maybe even standardize someday, what is feasible for us to actually implement and like provide guarantees for. And so he's part of a broader kind of informal working group called, I think, the Rust Spec Working Group or something, which is a few people from various universities around the world kind of like talking about trying to formalize Rust semantics regarding unsafe. There's also, I think, from Florian Gilcher, or his company, I forget what they're called, the new Rust Foundry?
I think
I might be wrong.
Remember.
But he has a company, a consultancy, doing Rust work in Europe, and part of that is a thing called sealed Rust, which the idea here is kind of like a very, like, if you want to use Rust in a, like, security critical industry, you want to have more assurances that unsafe code is safe than just, okay, trust us. And so the idea is to use formal methods to create a subset of Rust, and then only ever add new features to that subset when they have been proven to work in a safe way, using actual, like, proofs, and like they have been reviewed, and we think they're good.
I think there's a lot of academic interest in this area too, because Rust presents this interesting opportunity where you have a language that overall provides some pretty strong guarantees, like the linear types, or mostly linear types, is a pretty strong guarantee for the compiler to give you. And then you have these parts of the code that in theory uphold the same guarantees, and it's just a perfect opportunity to use formal methods. Mm-hmm. And so I think there's a lot of ongoing academic work in trying to find how can we prove unsafe code correct. Mm-hmm. And I think we will only see more of that in the years to come.
There's kind of a segue right there too to our next bullet point here, which is NLL has been turned on for Rust 2015. NLL, what is that?
Non-lexical lifetimes. So this, for those who have been with Rust for a while, many of you will remember that this was the big hype. For
December
many years,
of last year,
yeah,
it finally arrived.
For many years, there were so many weird tricks you had to play with your code in certain cases to get the borrow checker to basically understand what you meant and agree that your code was correct. And you had to play this weird song and dance to get it, to convince it. And then NLL was the big thing that was going to solve this. And it is essentially a smarter borrow checker. It is almost a theory of lifetimes that has been developed to capture many more convoluted lifetime patterns so that the compiler can reason about them and figure out that they're correct. And so December of last year, NLL...
The new edition came.
Yeah, the new edition came, the 2018 edition, and it included NLL turned on by default. This meant that basically anyone who picked up Rust after the 2018 edition didn't have to deal with any of these problems. The borrow checker most of the time just understood your code correctly.
So if they're new to Rust in the past, say, 6 months or so, this is not really news to them because they've been using new style Rust all this time. Yep. So mostly it's for Rust 2015 now. What is that?
So Rust 2015 is the original Rust, so to speak. Mm-hmm. There are a couple of differences. Many of them are syntax-based. But one of the big ones is that in the 2015 edition, NLL was turned off by default. So in the 2015 edition, you were still running with the old borrow checker. This meant that there was a lot more fighting with the compiler going on, much more so than people were working on 2018 edition code. It also meant that there were a number of known bugs in the old borrow checker, mm-hmm. where it would allow code through that was actually broken.
And we should mention, too, the old borrow checker is very old. It is the first version that was ever written. There maybe were some like research ones ever, but for Rust, it's their first version. And so there were some known bugs, and it's kind of like the people who wrote it certainly knew there were limitations at the time. And so there's plenty of really old open bugs on the bug tracker where it's kind of like, yeah, we know this is unsound. We're not going to try and fix it now because we're fixing it later by writing the entire thing. So a whole new, like, fresh rewrite that first required MIR to come on its own, and like a whole, like, tearing out chunks of the compiler itself, adding in new layers and levels. It was a massive effort over many years, like at least 3 or 4. To get this done. And so, yeah, it's finally here, and it's fixed many bugs. The problem is that bugs are sometimes relied upon to get things to work. And this is a problem that any language that's gone on long enough deals with. And so it's kind of like, are we allowed to break your code if we had a bug in our code, and you relied on our bug.
Yeah, so this is something that the Rust team has struggled a lot with. Like, what do we do in this case? Because if we switch everyone over to NLL, it's going to break existing code. And I think the middle ground they've arrived at is really cool. The idea here is that you have both borrow checkers built into the compiler. And so what you're going to do is you're going to run NLL first.
The new one.
The new one. And if the new borrow checker accepts the code, then everything is fine.
You're fine.
If the new borrow checker rejects the code, then you run the old one. And if the old one rejects it too, then you're fine. You can reject the code. If the new one rejects it and the old one accepts it, then you're in this weird territory where there's a known bug, but you're relying on it.
Mm-hmm.
And so what they've decided to do for enabling this by default for the 2015 edition is that code will still compile, but it will emit a deprecation warning saying that in future versions of Rust, this buggy behavior will not compile anymore.
Mm. And I should mention, too, the reason why we care about this is because the way that editions work in Rust, they aren't like fundamental forks of the language. The way it works is anytime a new edition comes out, what happens is that, Rust is, quote-unquote, the new version, but we maintain compatibility by compiling code, kind of transpiling code, from the old version into the new version, which, in one sense, limits what is even possible to change using the editions format like this, which is maybe a good thing. Kind of keeps things not like Python 3-esque, where only very kind of like small, automatic kind of changes. In this case, it wasn't really expected. Certainly when the language was written, we didn't think there was going to be any kind of code relying too much. And we do have tools to check for this. And so there's a tool called Iterator. It pretty much just, whenever there's a new version of the compiler, we can try compiling all the thousands of crates on crates.io. And if anything has changed from the previous result, like where a crate that formerly compiled stopped compiling, we can collect and log those. And so I think there were of all the 20 or so thousand crates on crates.io, about 80 crates, I think, were relying on this buggy behavior. And they often in the past, this has happened before too. This is actually mentioned. This is called out explicitly in the Rust compatibility guarantee statement. What things are allowed to break, bugs. We are allowed to break code to fix bugs, but just because we're allowed to break code doesn't mean we want to break code. We don't want to cause disruption because we don't want users to get mad at us and create noise. We want people to kind of be happy using Rust and have plenty of ongoing warning. So as part of this, I've lost the plot.
I think that's a good point, that in Rust, we don't want to guarantee that we never fix bugs. That would be a terrible backwards compatibility guarantee.
What I was going to say is that, when this happened in the past, often what the Rust team themselves will do is they will submit PRs to these crates, and then they will try and get them accepted before the new release comes out to try and minimize breakage in the wild, or if it does break, the idea is you can do a Krycho update, and I have new versions, it all just works.
So why was this change made now?
So, like we said, there's only one version of the compiler at any given time. And so there's not a 2015 fork and a 2018 fork. Because that's just there's too much maintenance burden. You can imagine in the future when we have say 10 years from now, we have 4 editions, we don't want to maintain 4 compilers. We want to be able to link old code from new code, and so we don't want to maintain 4 different ABI surfaces, or even 4 times 4. So the idea is only one compiler, and so we need to have the old borrow checker in there still, in the new compiler, in the modern compiler, to check for the old code. But we want to tear it out at some point. And I say we, I mean kind of just for us, the Rust developers, Rust everyone, part of the community. And to make it happen, because we love tearing out old code, we want to switch everyone over to the new borrow checker. Also, it's kind of just it is easier to maintain. It is more performant. It is less legacy, I guess.
Less hacks upon hacks upon hacks.
Yeah.
I think part of it is probably also that there's been a lot of work on the new borrow checker up through time. And I think it's now gotten to the point where it is just clearly better in basically every way. And so it seemed like a good time to move the 2015 parts over. Right? At this point, the new bar checker should accept any correct code from the old one, and all the rejects should be broken code. Mm-hmm. And so therefore, it just seemed like time, would be my guess.
Yeah.
The next feature on the list is one that I'm very excited about. It's a relatively minor feature, and it's really just fixing a paper
I'll let
cut.
you take this one, because I have no real experience with it.
Yeah, so Cargo gained a new flag called --offline. This is often referred to as airplane mode. And the idea here is, if you're somewhere where you don't have internet, and you are trying to build your Rust packages, previously Cargo would always try to connect to the internet. It would try to go to crates.io and download the latest versions. Even if you didn't run Cargo update, even just a Cargo build or something like that, it would still sometimes require you to be online. Even if it had an existing version of some dependency you had locally installed. And with the new --offline flag, what you're telling Cargo is, go look locally and use whatever version you find locally, assuming it matches Semver, etc. And if you can't, that's an error. This is combined with a new feature to Cargo called Cargo Fetch. And Cargo Fetch will download all your dependencies so that later when you run Cargo with the offline flag, it won't have to go to the internet. It'll fetch all your dependencies.
Very cool. And you kind of like, it's maybe a feature that not many know of, is that you can actually look at Rust docs for any crate you have on your computer offline using Cargo as well. So do you know the command for that? Cargo doc?
It's just Cargo doc.
Yeah.
You can give -p in the name of a dependency to get the docs for that dependency.
Yeah, and it launches a web browser for you right there using like locally sourced artisanal HTML.
And what this feature means is that we're finally now in a position where you can develop Rust without an internet connection.
Yeah.
You will have to download your dependencies at some point. You couldn't like go to a cave and then just like start writing Rust code if you wanted dependencies. But assuming you have dependencies locally already, at least now that workflow will work for you.
Mm-hmm. So we covered the Cargo changes and the language level changes. Now for library stuff, there's always a few new APIs, a few tweaked APIs. The tweaks this time are we've added const to a few of the APIs currently in std, and const means basically you can call this function at compile time. And so you can do some kind of computation totally before runtime ever occurs, before the user even gets your code. It's just there in the binary, the result of this function, which is really cool for plenty of things. That's kind of the ongoing constification of std as const gets more powerful. What's next? Write vectored. What is that?
Oh, so this is really neat. So the standard IO write and read traits have gotten new versions that are called _vector. And this is...
vector like the buffer, like vector T?
So it's not a vector T. It takes this thing called an IO slice, or it takes a slice of IO slices. But the way to think about this is, imagine you want to do a read and you have multiple buffers available to you. Then the way you could do this previously is you could allocate one big vector, read into it, and then copy from that vector into all the small buffers. But this means you're doing an extra copy for all the data you read. That is really inefficient. And so what read vectored lets you do is instead give the operating system a pointer to all the difference buffers you have available to you, and it will fill them up one after the other, and then tell you how many bytes it wrote into each one. And similarly for write, if you have data in multiple different buffers, rather than having to concatenate it into one buffer and then passing it to write, you can now just give it pointers to all the buffers you want to write out, and it will go into each one and write out the data for you, again saving you a copy and an allocation. And so these new APIs are really handy if you're writing high-performance I/O libraries or programs.
Yes, and as alluded to, it has nothing actually to do with the vector type in std. Mostly these names are from precedents in other languages, so unfortunate, but sometimes it be like that. There's a new API called Iterator copied, or a new copied function on the Iterator module, where previously have you ever called .cloned on any kind of iterator chain to kind of like get a clone of the things inside of it. Copied is the same thing, but it calls copy instead of clone. And so for data that implements copy, that can be more efficient this way. So again, kind of like eliminating some copies or some clones, say some allocations, which can also be good for core crates, no stud crates.
Yeah, there are also some other nice implications of this, like the compiler can now optimize that code for types that are copy.
Mm-hmm.
And furthermore, if you have a library that you know that it would be far too expensive to clone this iterator, but you'd think it would be okay to copy, you can now sort of give your code that constraint as well and let the optimizer work on it.
Yeah.
The other thing that's been not added but changed is the debug macro. So the debug macro was released, I think, in 134 or 135. And you can think of it sort of like a print line that is really tailored for debugging.
Mm-hmm.
So the debug macro, you can take any expression in Rust, you can surround it with the debug macro. It will still evaluate to the same thing, but it will also print out the value of that statement using debug, and it will print out the file and line number for that print. So it's a really convenient way to just sort of trace through what your program is doing, especially if you're trying to find some bug, rather than just putting print statements everywhere. The debug macro is really easy to just add and remove.
It's DBG, actually. Let's make sure we want to use it, yeah.
So the change that happened this time is now the debug macro also takes multiple arguments. So if you give it, you can give it debug XYZ with commas in between. And now it will print out the debug values for all of those inputs. And in addition, it will now evaluate to a 3-element tuple XYZ. So you can now call it and use it in any place where you have more than one variable.
Cool. Very cool. One last tweak we have here is there is people who have used result before might have tried a thing where you kind of like get a result, you have like, and then say you have an operation that returns result, but you don't really care what the result is. Often for doing I/O, you like write something, kind of just like say, okay, just write it. Like I care about the side effect really. There is a attribute on the result type called must use, which warns you if you do this. The idea being like, hey, actually, when you did this right, like even though you only care about the side effect, really you should check the error here. And so now must use is actually an attribute that can be used not just on types, but on functions. And 2 functions that have been added, or this attribute has been added to, are result is okay and result is error, which returned booleans previously, which you could also just drop on the floor and nothing would stop you. Now this will at least warn you, and you can turn, if you want to, all these warnings into a hard error in your crate. So, pretty cool.
Yeah, the idea here is that the standard library shouldn't let you ignore errors, but your code is free to ignore errors. Mm-hmm. And the way they enforce this now, or not really enforce, but the way they warn you about this is if you would have accidentally dropped an error, that it will tell you should probably handle this error. You can handle it by assigning it to underscore or something similar, but you need your program
to acknowledge it.
Yes, exactly.
Okay, cool.
I think those are all of the major changes.
Yeah, there was a lot this time, and so it's funny because the previous release, 1.35, had pretty much nothing interesting to talk about, as far as I'm concerned. So yeah, as for our first podcast, we had a whole lot of good meat to chew on this time. And so hopefully the goal is to do one of these every 6 weeks with every Rust release. So we'll have more or less to talk about. Maybe we'll do some interviews in the future. But yeah, this is a very kind of just, this podcast itself is very casual. As mentioned before, we want this to be kind of a community project. And so it's a radio station for Rust stations. So yeah, if you have, like, say, an idea for a podcast and you want to kind of just like get a microphone, throw it up, make a recording in Audacity and give it to us, theoretically, we should be able to kind of just like host it for you, kind of as a guest podcast. So yeah, feel free to get in touch with us on either our Twitter or our Discord. We're around. Yeah. And
in theory, you should be finding links to these in the show description, somewhere in front of, below, above, through, anywhere in your podcast app.
That sounds great.
Excellent. Thanks for tuning in, and we'll see you for the next Rust release.
Cool. See ya.